We have to start our session today. Today, our speaker is Professor Nasir Ganikhodjaev with a talk devoted to quadratic stochastic processes with a continuous set of states. Please.
Okay, thank you. Good evening to all of you. Well, first of all, I would like to thank organizer for including my presentation to this schedule of this conference seminar. So this is topic quadratic stochastic processes with continuous set of states. Already before I presented a little bit about quadratic stochastic operators and discuss the ergodic trajectory properties. So now I will try to construct some type of processes with such operators. So, no, first of all, what does mean stochastic operator? In general common definition. So we're considering a measurable space with pair, and let M be the collection of all probability measures. And we defined quadratic stochastic operator as a mapping of the set of measures into itself of such form. So for any measure mu, an arbitrary measurable set, we define its image of this measure like, sorry, here should be also x. So here x and also x. And this is a transition probability, pxyb, and iterating by this measure mu, initial measure. And this function pxyb should satisfy the following natural condition. First of all, for any fixed x and y, this is measure, probability measure. That is for any b from f, this is as b measure. And for fixed b, this function is will have symmetry. And as function of two variables, for fixed b, this is measurable function respect to sigma algebra, tensor product, algebra f to itself. It's clear, so from this condition, for any b, x, y, we have non-negativity b, and for whole x, we have 1. Since probability measure. So if the state space X finite set, and then corresponding sigma algebra is usual power set, then the set of all probability measures on this pair of finite X has the following form, that is, this is distribution on X, such properties. And the set usually is called a minus one dimensional simplex. And we can denote this is Pij dot, this is discrete measure on X, and should satisfy this condition. That is sum for respect to all K1. And we will, for simplicity, we denote this Pij like this tensor. And in this case, our operator will have such form. And usually, since such operators has some application arise from biologic problems, sometimes this Piaget is called heredity coefficients. So in the previous properties, we can rewrite in more simple form this usual sum equal to 1. Symmetry and non-negativity. So such operators, they can be reinterpreted in terms of evolutionary operator of free population, and such type such operator considered in such paper, no classic, I can say paper, Bernstein paper, so this the solution of mathematical problem related to the theory of heredity. Jenks, this he considered differential system of interactive populations. Heston, Lubitsch, and initially, and also Volterra. So I mentioned only these classical previous original papers. Now, of course, there are a lot of papers devoted to such topic. So now we will define quadratic separator as follows. The same again, XF is pair, measurable space, M collection. So now we will consider this transition probability, PXSXTA. This is probability of the following event. If states X and Y in X from X interact at time S, then one of the elements of the set A will be realized at time T. So here may be a little bit unexpected my suggestions. The realization of interaction in physical, chemical, and biological phenomena requires some time. We assume that the minimum of these values of time is equal to 1. That is, this transition probabilities is defined only when t minus a greater or equal 1. So, and this family of transition functions, we will call quadratic stochastic process if this family satisfy the following conditions. No, first of all, symmetry. Secondary, this for fixed x and y, we have probability measure. And here again, I assume so t minus s greater or equal 1. And for fixed a, this function, measurable function. So now this is natural assumptions. So now condition similar Kolmogorov-Chapman equations. So now in this case we have two types of such equations. For initial measure mu 0 in arbitrary this moments of times, which one satisfies these conditions, we have either this condition for A. So we can compute like this using this equality. Or second one for B, this is another equation. So here mu time B, mu tau B, this is measure which one defined like here. So now a little bit comment about these conditions. No, first, second, and third conditions, they are usual reformulation of similar conditions for transition probability of Markov processes, Markov chains. So now condition four analogy are the analogy of Chapman-Kolmogorov equations. So equation for A and for B, these two different equations, can be interpreted as different rules of appearance of the grandchildren. These equations have implication also for chemical treatments. So the appearance of particles in reactions passing in ordinary chemical kinetics are described for equation of type 4A, and equation of type 4B reflects the appearance of particles in processes of catalysis. So maybe, so here if come back, so how we can produce x, y, and element from A. From x, y, x1 parents, this is children. From these children, we're producing grandchildren. This one a little bit, I don't know, but maybe
So
unexpected.
I have one question. So this measure P, it depends on mu zero.
Yeah. Which one? P?
No, I mean PST, it depends somehow on mu zero, because you have mu tau there.
Yeah, this compute mu tau B.
So you
Start
consider
using
a pair,
P0
measure P S
XYTB.
X T A and mu tau
Because,
simul. So
yeah.
you have to study two objects.
No, I have family of these transition functions. Now, starting from some initial measure, some measure mu0, I try to define this Kolmogorov-Chapman equation. First variant, this one, and second one, this one, where mu tau, measure mu tau is defined as such way. That is why using this
I
transition
understand. Thank
probability,
you.
integrating by mu0. It's okay?
Yes, thanks.
Okay. So, so we have two type of Kolmogorov-Chapman equations, and then the process defined by this transition function, which one satisfy condition 1 to 3, is called quadratic stochastic process of type A if holds for A, and process type B if we have equality for B. And this condition about homogeneity. So here may be different type of homogeneity. So if we will have such equality for any t, when t greater than 1. So this one we can consider as homogeneity of transition functions per unit time. In general, from this condition does not follow homogeneity in general. Thus, a set of quadratic statistics operators one can decompose into following three classes. Homogeneous in usual means, that is depend only from difference t minus s. Homogeneous per unit time, that is transition for satisfies this condition for 5. And third type if percents don't belong to the second class. And the process from this third class are called, we will call non-homogeneous. So now, thus quadratic stochastic processes related to quadratic operator or quadratic transformation in the same way as Markov process are related to linear transformation. So by this reason, a number of concepts and problems of the theory of Markov process can be considered for such process also. So now we can consider establish some relation between quadratic and Markov processes. So this is a simple theorem session. So if we have if this family determine quadratic stochastic process of type A or type B and use M0 in initial distribution, then such value is integral by x, or respectively this one is is a transition function for some Markov process. That is averaging, we can construct Markov process. This simple calculations, how we can produce. So this integral, you are using Kolmogorov-Chapman equation here and iterating. Finally, we have this equality. So now a remark. So process generated by transition probabilities, this one, or respect to this one, be non-homogeneous Markov process, and it be homogeneous if only if corresponding quadratic process is homogeneous. Thus, starting from such process, we can present some examples of non-homogeneous Markov processes. So now follow this well-known paper of Andrei Nikolaevich Kolmogorov. We can we define, reduce some first and second integral differential equation using Kolmogorov-Chapman equations. So, for example, considering these differences, we can rewrite using Kolmogorov-Chapman equation like this one, and defining this C as a limit. No, provided the limit exists, we have such integral differential equation. Similarly, here t minus 1, that is, this is dilated, and here it s, here s plus 1, that is forwarded equation. So this difference between result for Markov chains. So now we can consider, we can introduce density for these transition probabilities. So let X be the set of real numbers, this AZ the set, and we defined Fsxdy as such value, respectively for second case. So this F and F tilde, they are distribution functions for quadratic process type of A and type B, respectively. And if functions f and f tilde are absolutely continuous with respect to variable z, then there are non-negative functions, that is densities, which one we can compute like this one. So then, with respect to such densities, Kolmogorov-Chapman equation one can rewrite as more simple form. This one, this one. And if measure has density, it is absolutely continuous, then these two fundamental equations for this respect to densities, we can rewrite as such form for type A and this one for type B. So now following, we can rewrite this our previous integral differential equation with respect to densities like this two equations, where this parameter AT computed this limit. So now, under some conditions to density functions, we can this differential equation reduce to uh, differential equations, but of course with delaying argument. So for first equation, using considering this increment and using Kolmogorov equations, we can have this equality, and no, here I'm following this Kolmogorov method. So now this function we can expand into Taylor series in the neighborhood of the point xy, assuming that this function have partial derivatives up third order. So substituting, we have to this Taylor series, and substituting this expansion into equations, we can evaluate the integral from the each summand. This integral 0, we can compute. This integral I can rewrite, assuming so as xy h, this is value. So step by step we can evaluate the integral. Consider this is first moment, second moment. So finally, we have solving differential this one. So this limit for these values, and finally we have such differential equation. And here this is argument t. Here again delaying t minus 1. Similarly, here what is this is for second one. So now I will try to define the Brownian interbreeding quadratic stochastic process. So if we will consider this family of densities with this density for respect to measure RT is fixed, does not depend from T, then we will produce, one can show, so this family satisfied to Kolmogorov-Chapman equation, that is, we have some process, and this process is homogeneous. So now I will call such this family of heredity probabilities one can consider as homogeneous Brownian interbreeding because this is a biological mean quadratic stochastic process. So this first example of such example process, and we can verify it is so this family satisfy both Kolmogorov-Chapman equation, both type and A and B, and you can see so this is homogeneous. And the second family, this one also satisfy. This is for such families valid. This is families process type A. And since here we have t plus 1, this family is non-homogeneous. So, and third example, also non-homogeneous, and this family also satisfy this process of type A. So, of course, I admit I will not consider all calculations. So, but I have checked. So this all three families satisfy this one to both Kolmogorov-Chapman equations. This one um, tab A and this one also tab A. That on the way, considering average of such processes, we will have non-homogeneous Markov process. So, so thus I can I introduce homogeneous and non-homogeneous Brownian interbreeding. I call this one is quadratic stochastic process. So let me stop here because remaining parts to consider more interesting substantive results, I'm not ready. Because this area for me, a little bit new. I'm only try mm, to study this one. But that is all from me. Sorry for short presentation, but here I'm not. I think no need to consider all calculations. So that is all.
Okay, thank you very much. And maybe there are some questions and comments, please. I have a question related to the following. As you mentioned, the origin source for such processes, for construction of such processes, is some genetics. Yes?
Yeah.
Okay. And in such very popular models like Wright-Fisher processes in genetics, we always can do the following scheme. We can start from some finite number of particles, then describe precisely the procedure of the splitting, birth, death, all these things, changing genotype, and after this we get the measure-valued process. But this measure-valued process will consist from discrete measures, namely from measures which contains only a finite number of particles. But after this, we can go to the limit in some sense. And in this way, we get a Wright-Fisher model. In this way, we construct irregular super processes, but they have not constant mass, and so on. So, is it possible in your model to have such approximation? So start from some few particles, get the processes which is supported by discrete measures, and then try to go to the limit.
Yeah, yes, of course. For when this I mentioned before, if state space is finite, I can repeat everything, but we will have system of differential equations, and we can investigate. But main problem here is so this you can see so all my equations, and they are differential equations with delaying argument. And here some difficulties. But my main goal was I have tried to Of course, I can consider here Poisson distribution, something in these BIOS processes and the other one. But here I try to discuss or to construct process which was close to Gaussian to diffusion. By this reason, I call this is Brownian or diffusion interpreting something like this one. This is because averaging we will have Brownian motion and some maybe some eligible differ, but in any case for finite set we can construct yes defined discrete measure and try to by using approximation. But I did not consider such problem. But this is really possible because I know how to, for finite case, to construct, reduce, produce, this, repeat all these calculations. And of course, we can try to after this to consider problem of sorry. And we can pass to consider limit. I think this is an interesting problem.
Okay, thank you. Maybe some other questions, please.
I would like to ask a question. When we consider, say, finite time Markov process, then its transition probabilities can be described via Kolmogorov equation, and the only thing you need to know is intensities, in transition intensities. And if you want to construct diffusion process, you have to know two functions, drift and diffusion. And if drift and diffusion are nice, then you solve parabolic equation and get transition probability of a Markov process. In your case, you have a delay, you have assumption t minus s is greater than 1.
Yeah,
But
yeah.
my question is it possible to find, or not to find, to give some functions like drift and diffusions or intensities, and say that if you have intensities, then there exists quadratic stochastic process.
Yeah. I think this is interesting, good questions. But since I already mentioned, so I am only now studying this topic. So I will try to do this things. But difficulties again this solving differential equations because this is the line argument in the so now I should well know how to solve some differential equations, the line argument, partial differential equations. So we have such equation.
Yeah. So my question is: assume that you have three functions n, please, n, b, a. I don't remember.
Yeah.
Then is there a quadratic stochastic process that satisfies all your assumptions?
No, Vessel, for this maybe inverse problem for such process, I can compute these parameters of differential equations.
Yes, I understand. But assume that parameters are given. Is it possible to prove that the process exists and is homogeneous or is satisfied for A or for B?
I'm not ready to give answer because this is good questions, but this maybe I need some time, a long time for to give answer.
Thanks.
Again, it looks related to possibility to solve such obtain an equation with delay. Yeah.
Yeah.
Mhm. Okay. So maybe some other questions, please. Okay. If there are no any questions, then for today we close our work. And Georgi, can you say who will be the next speaker?
The next speaker will be Katya Gliniana.
Okay, good. Thanks everybody and bye.
Okay, bye. Bye bye.
Bye.
Thank you. Bye.
Thank you, bye.
Комментируют.